Now for an example of this, let's take a look at R, in which I've got a data set ready to go, and for us to see how to calculate this. All right, so I've got a data set that I named data because I was not feeling very creative. But this is values for 22 different weights. This is a fictitious data set, so I'm going to keep it fairly fictitious. You can see that I have already computed the mean standard deviation of this data set. I also wrote the length, or I asked R to compute the length, just so you can see that there are 22 values there. So if I want to create a confidence interval, I need to take the mean, that's our sample mean of our data set, and I'm going to do the lower bound first. So I'm going to do the subtraction portion. Now I'm going to need to get the t critical value from our t table. So for us, since there are 21 degrees of freedom, I'm going to go to the row in my t table that says 21. And in general, we most often create 95% confidence intervals, and that's what we'll do for this moment. So I'm going to cruise on over to my t table. This is the one that was distributed in class. It is also posted on Canvas. So I'm going to cruise on down to 21 degrees of freedom. And, well, which number am I going to choose along that highlighted row? Recall, if we are having 95% confidence, that's the typical, then the tail region is 5%, but that 5% needs to be chopped in half. So it's tempting to go to the column that says 0.05, 5%, but we need to chop that in half. So I actually need to go to the column that says 0.025. So the value that I want is actually 2.08. And I believe I showed in class one day kind of the cheater mode. It's not really cheating, but on the bottom of the t-table, you can actually see that this column corresponds to the column that says 95%. So that's a nice check. Okay, so we've just said that our t-critical value is 2.08. So we're going to go 2.08 times the standard deviation for our sample data. And I know that the sample size is 22, so I'm just going to type square root of 22. This is going to be our lower bound. Maybe I'll give it a name. I'll call it LB. Recall, when you assign an object a name in R, it's not going to tell you its value. You're going to have to request it. But before I go and request what my lower bound is, I'm just going to go ahead and calculate my upper bound. Now, just giving it a new name doesn't really do much. I need to go turn this into a plus sign. Okay, so I am now going to ask R, please report my lower bound and upper bound for my confidence interval. There it is. So the calculations were not too extensive. A little review here, but this lower bound to upper bound is a way to estimate the population mean, right? We don't know the population mean in general. We might know the sample mean, and the sample mean is halfway in between these two values. This is an estimate for the population mean, and we are 95% confident. This is comment, a 95% confident that the population mean is between 14.0088 and 15.8389. Remember that the population mean is an unknown. We don't know if that population mean is in that interval. We don't know if our population mean is between these two numbers. However, if we were to repeatedly sample from this fictitious population, 22 weights, right, repeatedly, so sample of size 22, repeat, sample of size 22, and we were to repeatedly create confidence intervals from those samples, then we would expect in 95% of those confidence intervals, the population mean to be contained in that range. So we don't know if this particular random sample resulted in a confidence interval that contains mu, but we do know that this process should work 95% of all random samples. Additionally, there are some requirements for a confidence interval to be valid. And so let's discuss some of those requirements right now. Requirements. In no particular order. Since we are using samples to infer to a population, it is required that the sample be considered a random sample from the population. Usually that info is sort of described in the sampling protocol of a given problem. Secondly, we also require that the observations are independent. They are not influencing one another. So in this fictitious example, the weight of one organism is not affecting the weight of the next organism or the one before. Now, the one that may take just a little bit of work is that we need to consider the sampling distribution of the sample mean, y, capital Y with a bar, approximately normal. And that can be verified in one of two ways, or I suppose both ways. So if you were given some information that the original population is normal, so I'm going to say population Y is normal, then that would be satisfy that the sampling distribution of the sample mean should be approximately normal. However, if condition 1 cannot be satisfied, then we can utilize the central limit theorem. I'm going to use that a lot, so I'm going to call that CLT. Boop, boop. The central limit theorem states that if a population is not normal, then its sampling distribution still can be considered approximately normally distributed as long as you have a sufficiently large sample size. So, to abbreviate that a little bit, regardless of the distribution of Y, its sampling distribution will be approximately normal for sufficiently large sample sizes. And we had mentioned in our class just to kind of have a overarching condition for that. And we said if our sample size is at least 30. So how do we verify this? Well, again, random sampling. You'll be given some information about the sampling protocol. You're looking for that word random. Observations independent. That may require some knowledge of the field and how that variable or that population works. But again, for the purpose of our course, we will just assume that that is true, or I may be giving you that information again in the sampling description. The one that takes a little bit of work is this third bullet point here. So how do we know, how can we check that the population is normal? Well, if we have the data set available like we do in R, then what we can do is make a QQ plot and see if that QQ plot validates or if that QQ plot shows that we have an approximately normal distribution in the sample, which then can be inferred to the population. Now, if that QQ plot does not show us what we want to see, in that it does not appear normal, then do we get to go and check out the central limit theorem. So the central limit theorem only needs to be invoked if that QQ plot does not show us a normal distribution. So let's go back to R and see how this plays out for the fictitious weight data set. So I'm going to assume that the first two conditions are met. But let's make a QQ plot. The function in R is QQ norm of our data. Very good. So recall, if you do QQ norm and then do QQ line, you'll get sort of a reference line there. What we generally want to see is mostly a straight line. And while this is not perfect, this is within reason that we can assume that this distribution came from a normal population, normally distributed population. Now, you may notice the sample size, recall, was a 22. That is certainly less than 30. But we didn't even need to consider that because the data set does look approximately normal. So again, the central limit theorem really only plays a role if this first condition cannot be met.